So let's think about energy changes in calorimetry. As a chemist, we are interested in two types of energy change. The first one is the change in potential energy of my system, which is the chemicals involved in the reaction. Unfortunately, we can't measure potential energy directly. So what we can do is measure another type of energy, which is the thermal energy in the surroundings. Because I know that an increase in one of them must lead to a decrease in the other, and vice versa. So if I can measure the change in thermal energy in the surroundings, I can work out what change in potential energy there must have been in the system. Let's take a look at the two common examples that you might see in a chemistry course. The first example might be a combustion reaction where I am reacting a chemical with oxygen in the air. Let's take a spirit burner containing a fuel that has been lit so that it's reacting with oxygen in the air. So the system, in this case, is the chemicals involved in my reaction, which would be the fuel, oxygen in the air, and the products, which might be carbon dioxide and water. So what then are the surroundings? Well, in a common chemistry experiment, you will place a beaker of water over the top of that reaction, and we are then going to assume that the water, in this case, is my surroundings. And why do we make this simplification? Well, if I stick a thermometer in my beaker of water, I can now measure changes in thermal energy in that water by measuring the change in temperature. Therefore, any thermal energy increase in the water must be because of a potential energy decrease in my chemical reaction. Now, this is certainly not a perfect assumption, because if I look at where my chemical reaction is happening, i.e. the flame is not totally surrounded by water. So a lot of that energy is probably being released to air and also to some of the equipment, such as the beaker itself and maybe the spirit burner. Let's now look at a second common example in chemistry. In this example, let's consider a chemical reaction that's occurring in a solution. So there's my beaker of water, and let's add some reactants. We'll make them all yellow for simplicity, and the products, which we'll make red. So in this case, what is my system? Well, as per usual, the system is the chemicals involved in my reaction. So in this case, it would be the yellow and red particles. And given that these are reacting in a solution, the surroundings in this case is my water. So, as in the first example, if I want to measure changes in thermal energy in my surroundings, which is the water, all I need to do is stick a thermometer into my solution. Now let's imagine during this reaction the temperature of my water decreases, indicating that the thermal energy in the water has decreased. That must mean that the potential energy in my system must have increased. Again, in this example, we are making quite a large assumption that my surroundings are only water. But of course, the beaker and also the air around the beaker technically are also surroundings. But the process is still accurate enough for its use in high school chemistry. Let's now summarize the key points from this video. Firstly, calorimetry is used to calculate energy changes, specifically in the potential energy of my system. And remember, by system, I'm talking about my chemical reaction, the reactants and the products. Unfortunately for us, this can't be measured directly. But what we can do is measure changes in thermal energy in the surroundings, because we know that any changes in the potential energy of the system must also equate to changes in the thermal energy in the surroundings. If one of these types of energy increases, the other must decrease, and vice versa. Hopefully, this video has been of some help.